Good morning, guys. Good afternoon. Good evening. So now, this is forces between, like force rather, force between two electric charges, which is Coulomb's law. Now, but before I deal with that, no, I will be dealing with three things today: method of charging, rubbing to be precise, Coulomb's law, and electric field. So do well to finish the video. Also like and subscribe and drop a comment. Thank you. Now, method of charging, rubbing to be precise. Why am I dealing with that? Because I just want to give a code. Whenever you are rubbing a glass rod with stick or a 4 with plastic rod. Are we together? Whenever you are rubbing, you can either rub a glass. Usually, a glass rub is rubbed with silk, while a 4, F stand for 4, is rubbed 4 or wool or hair. Either of the three, 4 or wool or hair is rubbed with plastic rod. So whenever you are rubbing either of these with any of those two things, these two will always be positively charged. So this is the code GF plus plus, like girlfriend plus plus. It's not good to have girlfriend. I just use it as a code. GF plus plus. GF plus plus. Addition of girlfriend, like girlfriend plus plus. Are we together? So whenever you are rubbing a glass rod with silk, you know the glass rod will be positively charged, meaning that the silk will be negatively charged. Whenever you are rubbing a fur or hair or wool, fur, are we together? Whenever you are rubbing a fur with plastic rod, the fur will also be positively charged, which means the plastic rod will be negatively charged. So that's that for that. Now let's move to force between electric charges, which is Coulomb's law. Now, 3-point charges, Q1, that's the question on the screen. You can pause the video and write it down. Now, we know that F, the magnitude of this force, F equals to K Q1 Q2 over what? Over R squared. Magnitude is magnitude. The force of electrostatic repulsion or attraction between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So that's that for that. But let's draw it. 3-point charges, we are given x axis on the x axis. So I'm having it like this. Let me just add the y-axis. There's no problem. This is my plus y, negative y, plus x, negative x. So 3-point charges Q1 5.0 nanocoulomb, Q2 1.0 nanocoulomb, Q3 negative 3.0 nanocoulomb are located at 0.00 centimeter, 2.0 centimeter, and 4.0 centimeter. That means this Q1 is located at the origin. Q2 is located at 2.0 centimeter on the x-axis. Q3 is located at 4.0 centimeter on the x-axis. So these are the origin. We have our Q1 here. Q1. What's the Q1? 5.0 nanocoulomb. Are we together? Let's say from here to here is 2.0 centimeter. This is the point 2.0 centimeter. Now turn it to meter. That means you are dividing it by 100. So that will give you 2 times 10 raised to power minus 2 meter. Are we together? Let's say this is the point 4 centimeter. This is our Q2, which is what? 1.0 nanocoulomb. This is our Q3, which is what? Negative 3.0 nanocoulomb. This one is at the point 4 centimeter. Divide it by 100 by, so that means you are converting to meter. It must be in meter. 4 times 10 raised power minus 2 meter. Are we together? So what are we doing next? Sorry. So now let's move. So all those charges they are on the x-axis. That's why I do not include the y-axis. All the three. This one at point 0 Q1, Q2 at point this, then Q3 at this particular point. Now we have to calculate the total electric force. Eh? Total electric force. You can see the arrow. You can see the arrow on that force. This arrow is telling you you have to find the direction too. Are we together? Exerted by Q2 and Q3 on Q1. So that means the force exerted by this Q2 and this Q3 on this one. That is the force that both of them, Q2 and Q3, are exerting on Q1. Are we together? That's what we want to consider. You are not to consider the one that Q1 is exerting on any or whatever. What you have to consider in the question is the one that Q2 and Q3 are exerting on Q1. Are we together? Now, first find the one that Q2 is exerting on it. So that means you are going to use F equals to K Q1 Q2 over R squared, which is what? Our K is 8.89 times 10 raised power minus 9. Okay, sorry, that place is too shallow, can't contain it. So we have 8.89 times 10 raised power minus 9. Are we together? Times what's our Q1? 5. This nano coulomb. Nano means 10 raised power minus 9. Don't forget. So that you convert it to coulomb. 5 times 10 raised power minus 9 times what's our Q2? 1. 1 times 10 raised power minus 9 over R, the distance between Q1 and Q2, from the origin to 2. That means the distance is 2. From here to here equals to 2 times 10 raised power minus 2 meter. Are we together? 2 times 10 raised power minus 2 meter. This point and this point, the distance between them is, are we together? So, but you are squaring it. That's 2 times 10 raised power minus 2 square. So this guy is going to give you what? At the end of the day, you are going to get 11.24 times 10 raised power minus 4 Newton. That's the force. That's just the what's it called now? The magnitude. Now for the direction, this is just the magnitude of the force. But for the direction now, Q2 is positive and Q1 is also positive. Are we together? So when you have like charges, what happens between them? They repel. That means the force that Q2 is exerting on Q1 will be repelling Q1, will be pushing Q1. So if I'm talking of pushing, if this is pushing this, that means Q1 is going to be pushed to the negative x-axis. So that's 11.24 times 10 raised power minus 4 along or towards along the negative x-axis. Along the negative x-axis. That's the magnitude and the direction. This is the magnitude and this is the direction. One word, that's the vector of the force exerted by Q2. Are we together? On Q1. So that's one. Now the force exerted by Q3 on Q1. The force exerted by Q3 on Q1. That one is going to give you F equals to K magnitude of Q1, Q3 over what? R square, which is what? 8.89 times 10 raised power minus 9 times, what's our Q1? 5 times 10 raised power minus 9. It's nano. What's our Q3? Minus 3 nano coulomb. You don't need the minus. We are finding the magnitude now. So you can see absolute value. So you don't need the minus in the calculation. Times, just use the 3 direct. 3 times 10 raised power minus 9 over, what's the distance between Q3 and Q1? From here to here is 2. From here to here is also 2. That's from here to here is 4. This 4. So, and it's in meter. That is 4 times 10 raised power minus 2 meter square, R square. So at the end of the day, this guy is going to give you um it's going to give you 8.43 times 10 raised to power minus 5 Newton. That's the magnitude. Now for the direction. You can see that Q3 is negative, Q1 is positive. What kind of force will happen between them? It's attraction. Like charges repel, unlike charges attract. They are unlike. So the force that Q3 is exerting on Q1 will be coming towards here because Q3 will be trying to attract Q1. Are we together? So it will be pulling it rather towards the positive x-axis. The force that this guy is exerting on this guy is towards positive x-axis. Are we together? This one is along negative x-axis. This one is along positive x-axis. Now that's not yet the final answer because we have to find the net force, the total force that is exerted on this, the net, the resultant. Because this one is pushing it away, Q2 is pushing it away, Q1 is attracting it back. So it will Q1 will surely fall on one side at the end of the day. For instance, if you have a box and a force is pushing it with 3 Newton, another force another force is pushing it back with 2 Newton. At the end of the day, this box will be moved towards this side because the one that is bringing it to this side is higher than the one that is taking it back. So at the end of the day, the net force on this box will be 3 minus 2, which is what? 1 Newton. So also the net force now, the net force F net on Q1, the net force on Q1 will be, this guy minus, you are not hard in this time. There are times we add, but it depends on the direction. The net force now will be what? The force that, Q2 exert on Q1 minus the one that Q3 exert on Q1. Why? Because those two forces are moving in opposite direction. This one is pushing it to this direction. This one is attracting it to this direction. They are opposite, so you are subtracting. If they are pushing it towards same direction or pulling it along same direction, you are adding. But so far, the direction at which they are acting on Q1 is opposite. You are going to subtract. So this guy is going to give us 11.24 times 10 raised power minus 4 minus 8.43 times 10 raised power minus 5. So the total force exert on Q1, F net on Q1 will give you what? That should be 2.809 times 10 raised to power minus 5 Newton. That is just the magnitude. That's just the magnitude. Are we together? Now for the direction, the question, there's an arrow on this. That's for the direction. Now, at the end of the day, which side will this Q1 go? This one is pushing it to negative x-axis with this amount, 11.24 times 10 raised by minus 4. Why this one is attracting it to the positive x-axis with this magnitude, 8.43 times 10 raised by minus 5. At the end of the day, Q1 will be pushed towards this side because the one that is pushing it to this side is bigger than the one that is attracting it to this side. So at the end of the day, it will go to this side. Are we together? It will go to the negative x-axis because the one that is pushing it to the negative x-axis is bigger than the one that is attracting it to the positive x-axis. So our final answer will be 2.89 times 10 raised by minus 5 along or towards along the negative x-axis. So that's our final answer. Are we together? That's the final answer. So we are done with that. Please take note of that. Please take note. Very, very important. So because of our time, the next one I'll be dealing with now, and you can change this one to 28.09 times 10 raised power minus 6, which is something as 28 Newton, 28.09 micro Newton. Anything times 10 raised power minus 6, that's micro. So either of the two. So that's that for that. Now another one we'll be dealing with is this electric field. Electric field. So electric field. This electric field intensity, the formula is electric force per unit charge, where the E is the electric field intensity. Electric field intensity, the unit is Newton per Coulomb. The electric force is Newton, while the quantity of charge, the unit is C. Now, there's a negative charge particle of 0.032 Coulomb in the free space. What are the magnitude and direction of the electric field 2.0 meter away from the particle? Now, what's your Q? Your Q equals to 0.32 Coulomb. What's your R? Distance, 2.0 meter. What are you asked to find? Magnitude and direction of the electric field intensity. Magnitude and direction of the electric field. So your E Are we together? E, by putting this arrow, I'm signifying the direction too, is equal to what? Unknown. So now what are we going to find now? So the next thing we are going to find here, we know that E equals to Fe over Q. But in this question, we don't have F. We only have Q. We don't have F. We only have Q. Are we together? There is no F. And we have R. So what do? We know that from Coulomb's law we discussed earlier, F equals to K Q1 Q2 over R squared. One of these Q is source charge, another one is test charge. The one here is test charge, test charge. One here is source charge, one here is test charge. Are we together? So now we are going to substitute this into F here. So at the end of the day, we have E equals to F. What's our F? K Q, going to give us K Q1, KQ. Okay, let me just KQ, then small q. One of them is our Q1, one of them is our Q2 over R squared. That's Fe divided by Q. This E equals to F over Q. E equals to F over Q times 1 over what? Q. Are we together? Times 1 over Q. So this test charge will cancel the test charge. So what do we have now? Our E equals to what? KQ over what? Over R squared. KQ over R squared. So our Q here is 0.32 coulombs. Our R here is 2 meter. Are we together? So at the end of the day, we are, our K 8 point what? 89 times 10 raised power minus 9. Our Q equals to 0.32 over what's our R? 2 meter square. So at the end of the day, we are going to get, let me punch my calculator. Um, I'm coming. So at the end of the day, we are going to get something like 7 7.2 times 10 raised power 8 Newton per coulomb. That's the magnitude. But the direction, the charge is negative. There's a negative charge particles. Yeah, the charge is negative. So what will be the direction of this field towards a negative charge? Listen, when you have normal a field, if you have a field like this, the direction of field is away from positive charge. Saying this is a positive charge, the direction of field will be away from it. Will be away from it. Are we together? Will be away from it. For a negatively charge, for a negative charge, the direction of field will be towards it. Will be towards it. Are we together? The direction of field will be towards it. So now, if you have to find the direction of this guy, it will be towards towards the negative charge. Towards the negative charge. Towards the negative towards the negative charge. Towards the negative charge. So that's the direction of the field. Take note. Direction of field will always be away from positive charge but towards negative charge. And since the charge is negative, the direction of the field will always be towards the negative charge. So this is our final answer. Please, maybe you can pause the video or go back and watch this aspect again so that you can understand. Now, the last question we'll be dealing with, calculate the electric. So this is the next question. Calculate the electric field, the vector and the net magnitude of charge. This Q equals to negative 0.005 microcoulomb on the origin 00 of a coordinate system at a point 1, 2. So we all know that this guy equals to KQ over R square. Are we together? So which is what? Our K. Sorry, I used 8.89 for K for those previous solution. It is actually 8.99. I'm sorry for that. 8.99 times 10 raised per minus 9. What's our Q? What's our Q? This is the 0.05 times 10 raised per minus 0.005. Sorry, 0.005. 0.005 times 10 raised per minus 6 over what's our distance? How do we find our r? The vector r, will give you x2 minus x1 plus y2 minus y1. So this j and this I. So your x2, this x1 y1 and this x2 y2. X1 y1 x2 y2. So x2 minus x1 1 minus 0 I plus 2 minus 0 plus 2 minus 0 j. At the end of the day, this is going to give you I plus 2j. That's the vector. But for the magnitude, it's going to give you root I square plus 2 square, which is what? Root 5. Root 5 meter. So this is going to give us root 5 square. So this is 0.005 times 10 raised by minus 6. So if you do everything with your calculator, you are going to get the magnitude of this E. The magnitude is going to give you 8 point. It's going to give you 8 point. I'm coming. Let me punch my calculator. 988 n per c. That's the magnitude. For the direction, include that negative sign in this cube. Include it, please. Include it for the direction. 8.988 multiplied by the unit vector. That's the vector, rather. The vector. The magnitude and the direction, not just the direction. So this is the vector. And please take note, you may have your answer like this, and probably, I don't know, your answer can be in another form. This is the form I'm referring to. Your unit vector equals to this over your magnitude. Your unit vector is equal to your vector over the magnitude. Are we together? And you know this one is I plus 2j. Right, communicating I plus 2j. And this magnitude is root 5. So your unit vector is something as I plus 2j over root 5. So at the end of the day, this guy, this particular one, can give you something like minus 8.988 times, what's your unit vector? I plus 2j over root 5. Do you understand? So that's that for that. Now, the last thing we'll be talking about, you need to know this. This is a source charge. This is a test charge. So we are talking of two things here: the direction of the field and the force exerted on the test charge. The direction of the field, always relate it to the source charge. Relate it to the source charge. The force exerted is on the test charge. So since this is positive, you know direction of the field will be away from it, away from it. And the force exerted by the source charge on this test charge is a force of repulsion because they are plus plus. So the force will be towards the test charge. Are we together? So the direction of the field and the direction of the force exerted on the test charge are in the same direction. The same, you can see they are the same direction. This one too, this negative, the direction of the field will be towards it for a negative charge. I'm sorry, towards it for a negative charge. So this minus this plus the force exerted by this source charge on this test charge is a source of attraction because they are unlike charge. So it's going to attract this one. Are we together? So yet when you have a negative source charge and a positive test charge, the direction of the field will still be in the same direction of the force exert on the test charge, still same direction, just like the first one. So the third one now, when the first charge is positive, when the source charge is positive and the test charge is negative, the field will be away because it's positive. The field will be away. The field will be away. But this negative is going to attract it, right? It's going to attract it. The force exerted by this on this is a force of attraction. Are we together? It's going to attract minus q because they are unlike charge. So the direction of the force exert on the test charge is in opposite direction with the field. Always relate the field to the source charge, not the test charge. For the field, relate it to the source charge. You can see I'm not drawing any field here that is inward or outward. I'm using the source charge for the direction of the field. Relate your source charge to the direction to the field, to the source, and your field to the source charge rather. While the force exerted on should be on the test charge. So this is opposite. For the last one, the source charge is negative, so the field is going to be inward, inward, inward. The test charge is also negative. The force exerted by this and this is force of repulsion because they are like charge, minus minus. So it's going to push the test charge. It's going to repulse it. Are we together? So this is still opposite. The direction of the field related to the direction of the force exerted on the test charge is in opposite direction. So please, you can preview the video. You can back it. And these four things I discussed last, take note of them very well. Thank you very much. Please do well to like, subscribe, and comment. See you in the next video.